For a long time, humans have wondered about the existence of alternate universes and life beyond our own world. Thanks to the James Webb Space Telescope, JWST, the most advanced observatory ever built, we may finally be closer to answering these questions. By observing Proxima Centauri, the star system nearest to ours at just 4 light-years away, scientists have detected unusual signals coming from one of its planets, Proxima B. These signals, called artificial illumination, have sparked great interest among researchers. But what do they really mean? Could these lights indicate the presence of intelligent life? Join us as we explore the JWST's fascinating discovery of what appear to be city-like lights, a finding that could transform our understanding of life in the universe. Currently, Earth is the only planet known to harbor life. Since ancient times, humanity has asked whether life exists elsewhere in the cosmos. To pursue this question, American astronomers Jill Tarter and Thomas Pearson launched a search for extraterrestrial intelligence, SETI, project in 1984. This project aims to detect alien radio signals, as radio waves can travel vast distances and be captured by the 42 radio telescopes of the Allen Telescope Array in California's Sierra Nevada mountains. However, no confirmed extraterrestrial signals have been found to date. The successful launch of the JWST has intensified efforts to study exoplanets, planets orbiting distant stars. Positioned about 1 million miles from Earth and equipped with highly sensitive instruments, the JWST is the largest space telescope ever constructed and holds tremendous potential for groundbreaking discoveries. While no exoplanets were known before, over 4,000 have since been identified, according to NASA, suggesting the universe may be home to millions more. Signs of extraterrestrial life could appear in alien vegetation. For example, the Galileo spacecraft, while en route to Jupiter, turned its instruments back toward Earth and detected a clear sign of vegetation known as the vegetation red edge. This biosignature results from a combination of red and infrared light reflected by plants. A planet covered in dense plant life, like Earth, would show a strong red edge signal. The JWST seeks to measure the red edge on distant Earth-like planets located in their stars' habitable zones, offering important clues about conditions beneath their atmospheres. When sunlight passes through a planet's atmosphere, certain frequencies are absorbed by molecules and particles, creating a unique spectral fingerprint that JWST can detect through spectroscopy. This method can reveal the atmosphere's composition and help determine if life could exist there. Earth-sized planets with atmospheres similar to ours, containing oxygen, nitrogen, and carbon dioxide, are promising candidates for life. By identifying unusual compounds like chlorofluorocarbons, CFCs, which are human-made chemicals used in refrigeration and cleaning, the JWST could even detect signs of technological civilizations. If CFCs were found in an exoplanet's atmosphere, it would strongly suggest advanced life forms. It's important to note that extraterrestrial life might not resemble life on Earth. Some organisms, such as extremophiles, microbes that thrive in harsh environments intolerable to most life, could appear alien. These microbes can survive extreme temperatures up to 250 degrees Fahrenheit or highly acidic conditions with pH below 3. Since Earth-like planets with stable orbits and temperatures suitable for liquid water are more likely to support life, initial searches focus on these worlds. Our Sun is classified as a yellow G-type star. These stars are relatively less common and typically have shorter lifespans. However, in the broader universe, the chances of studying planets orbiting red dwarf stars, which are more abundant and have lower luminosity and temperatures than the Sun, are higher. This longer lifespan of red dwarfs provides an extended window for the potential development of life and the evolution of complex organisms. Approximately 40 light-years from Earth lies the TRAPPIST-1 system, which will be the focus of the James Webb Space Telescope's JWST first mission. This system orbits a calm red dwarf star and contains 7 Earth-sized rocky planets. Notably, 3 of these planets lie within the star's habitable zone, meaning they could harbor liquid water on their surfaces. Despite being smaller and cooler than our Sun, TRAPPIST-1 emits light somewhat similar to that of our Sun, and due to the close orbits of its planets, it presents intriguing possibilities for habitability. One of the most promising candidates for detecting city lights beyond our solar system is Proxima Centauri, a red dwarf star located just 4.25 light-years away. Proxima Centauri is much dimmer than the Sun, so any potentially habitable planet would need to orbit much closer than Earth does to the Sun to sustain liquid water. In August 2016, astronomers discovered Proxima B, a planet with about 1.3 Earth masses located in this Goldilocks habitable zone where conditions could allow liquid water to exist. Proxima B orbits extremely close to its star at only 4.66 million kilometers, exposing it to intense solar winds that might strip away its atmosphere. Despite this, it receives enough sunlight to maintain temperatures that could support liquid water. Similar to Earth, the planet is believed to be tidally locked, meaning it always shows the same face to its star, much like the Moon does with Earth. Proxima Centauri itself has roughly 18% of the Sun's mass and emits just 5% of its brightness. Though Proxima B might appear barren or scorched, liquid water could still exist if it retains protective atmosphere to trap heat. Since it receives only about 65% of the solar energy that Earth gets, the planet might not be especially hospitable. Yet, its tidal locking creates permanent day and night sides, causing extreme temperature differences. Proxima B is also subjected to nearly 3 times the high-energy radiation, such as X-rays and ultraviolet light, that Earth experiences due to solar flares from its nearby star. Without a magnetic field similar to Earth's to shield it, these harsh conditions could be detrimental to life. Nonetheless, favorable conditions might still exist. Atmospheric models suggest that tidally locked planets face challenges, like volatile gases freezing on the dark side, which can break down the atmosphere. On Earth, volcanic activity helps replenish the atmosphere, and a strong magnetic field reduces atmospheric loss. Since we currently lack detailed data on Proxima B's volcanic activity or magnetic field, it's difficult to confirm whether it retains an atmosphere. An atmosphere would imply the presence of liquid seas, which in turn increases the potential for life. Scientists are hopeful about discovering whether Proxima B supports a complex biosphere. Some speculative ideas include solar power stations on the planet's day side to generate energy for lighting and warming the night side, making it more hospitable. The discovery of Proxima B has intensified efforts to detect if the planet passes in front of its star from Earth's perspective. Such transits would allow researchers to measure the planet's size and mass accurately, assess its density, and confirm its rocky nature. Observing starlight filtering through its atmosphere during a transit could reveal atmospheric composition. However, the probability that Proxima B's orbit aligns for a transit observation is only about 1.5%. Additionally, the star's frequent eruptions complicate these observations. Astronomer David Kipping of Columbia University notes that the star's behavior poses significant challenges for confirming and studying Proxima B's characteristics. Solar flares create instability as they cause rocky planets to absorb sunlight and re-emit it as infrared radiation. However, rocky planets emit a specific type of infrared light when orbiting stars like Proxima Centauri. The James Webb Space Telescope JWST was expressly designed to detect this infrared radiation. Proxima B's infrared signature is crucial for studying its atmosphere. Thanks to JWST's superior infrared capabilities, far exceeding those of the Hubble telescope, it could potentially detect city lights on Proxima B's night side, even if they are as faint as Earth's. If artificial lighting on Proxima B is limited to a narrow frequency band distinct from the star's light, JWST could identify it. Proxima B's day side might be extensively covered with solar panels that reflect starlight. Due to its orbit, the planet experiences a fixed pattern of day and night, with extreme temperature differences. If Proxima B lacks an atmosphere and is made entirely of exposed rock, temperatures on the day side would fluctuate greatly, radiating all absorbed energy as blackbody radiation, while the night side would become a frozen wasteland. Conversely, if temperature differences between day and night are less severe, it would indicate the presence of an atmosphere. JWST will need just 11.2 Earth days to collect sufficient data to detect potential artificial city lights on Proxima B's night side, lights that could suggest the presence of intelligent life beyond our solar system. Based on current studies, Proxima B might hold hidden secrets. Its day side could produce abundant solar energy, and the observed lights might be evidence of a technologically advanced civilization. Although detecting artificial lighting on Proxima B would be a groundbreaking discovery, scientists are cautious. Such signals could stem from natural phenomena such as reflections from surface features, volcanic activity, lightning storms, or unusual atmospheric effects that mimic artificial light. Since JWST's technology for examining distant worlds is still emerging, astronomers are refining their methods carefully. Ongoing observations by JWST will continue focusing on Proxima B and other potentially habitable exoplanets to better understand their atmospheres and surfaces. If artificial lights are detected, confirming their origin would require years of further study. Should these signals indeed indicate intelligent life, it would rank among humanity's most profound scientific revelations. The interest in Proxima B and similar exoplanets goes beyond the search for alien life. It raises deep philosophical questions about humanity's place in the cosmos. Discovering extraterrestrial civilizations could challenge the uniqueness of life on Earth and inspire unprecedented global unity through shared wonder and purpose. It would also underscore the vital importance of ongoing space exploration, motivating technological advancements to push humanity further into the cosmic frontier. Currently, the search for artificial illumination on Proxima B remains an exciting prospect that might soon provide answers to the age-old question of whether we are alone in the universe. As JWST sends back increasingly detailed data, the hope of detecting advanced life grows stronger, bringing us closer to solving one of science's greatest mysteries. If Proxima B does harbor an advanced alien civilization, this discovery could become the foundation for future breakthroughs in astrophysics, planetary science, and interstellar communication. As our knowledge expands, the next generation of researchers and explorers may finally confirm what once seemed impossible: that life in diverse forms is far more common throughout the universe than ever imagined.